I'm Phil, and we're going to look at the second video in the ALF series. So in the first video, we discovered what ALF was, and we found out that it was a road testing machine that had a big impact on the recent history of civil engineering road research, not only in Australia, but internationally. And it was able to assist in the development of new pavements for roads such as freeways. So what we're looking at in this video is simulating the lateral behaviour of traffic in a lane. Now, a lane width can vary from 3.3 to an upper limit or lower limit of 3 metres to 3.5 meters, depending on the speed. And where the lateral position of a vehicle is in the lane changes. And most of the time, it'll be in the center of the lane. So in the zone, up till one standard deviation, left or right, we've got about 30% of cars in that area. In the next zone, which is 2 standard deviations away, we've got an additional 13.6% of the vehicles will be in that area on the left and a similar number on the right. And this behavior is described in a statistical graph called the normal or Gaussian distribution. And this is what I'm going to simulate on my ALF model. So we'll go and have a look at that. I'm also going to look at the conservation of energy. So what we did and what happened on ALF, we used a trolley, and I'm going to replace that with a ball. And the trolley went up and down, but it went on 2 different set of rails, and it lifted the trolley on the second rail to ensure that it returns safely to an original position, and the potential energy was converted into kinetic energy and given a boost by the electric motor on ALF. This is quite similar to what's on this diagram on the top, where we've got a small electric motor that adds a bit of a boost to the ball, and the ball goes around in this cycle. On the bottom is similar to the loading cycle of the trolley on ALF, and then it returns back to the starting position. And there's 2 projects. The first one will be on ALF itself. The second one will be how I generate random numbers. So the ALF model that I've created looks like this on my desktop. First of all, the problem. Problem is that traffic is getting heavier and heavier, and it's also getting longer and longer. So if you look at what we have today, we've got multiple trailers, and it's gone from 2 to 3. And what's interesting is to see, is this having an impact on the life cycle and the design of roads? Okay, so my ALF model looks like this. I'm using a small device that allows me to move my truck in a lateral direction. And it's going to do this movement randomly to try and simulate the behavior of real traffic. So here's the total setup. I'm driving the stepping motor that provides a conversion from rotary to linear motion using a small computer, and they're connected with a hat on top of the computer so that we can get communications between the control computer and the computer that's embedded in the step-in motor. And before I did this, we actually had a model 43 years ago that was created as a memento of ALF. So this is now in pieces and no longer works. And it demonstrated the longitudinal control, or the longitudinal behavior, where potential energy was converted into electrical energy, potential energy was converted into kinetic energy and given a boost also with an electromagnet. So I'm going to replace that older model now with a upgraded model that uses the same principle, but instead of a trolley, it's going to use a small metal ball, and it's going to go through the cycle, and again boosted with the energy from an electromagnet. And here's another one, which we'll show in the demonstration. Okay, so the objective, we might increase the font on that, is to simulate the lateral control of ALF. And that is what we're interested in doing, is creating a random position in the uniform distribution. So I'm not using the Gaussian distribution in my model this time, but I'll do that in the next version. So I'm going to move the motor, and I'm for linear movement. And I'm going to use buttons to start and stop the procedure, and it's going to count the number of passes, just like on the real ALF. And I'll print the results on the serial monitor. The second part is that I want to demonstrate the random. Let's have a look at it. I want to demonstrate the use of the conservation of energy on ALF, and I'll also give it a gentle push, just like on the original ALF machine. Design-wise, I'll be using buttons and a step-in motor, and the background to all of this includes a knowledge of random numbers and how to create a random number. Hardware-wise, I'm going to use devices from M5Stack, and my computer is the StickC computer. And on top of the computer is an RS-485 hat that looks like this. See if we can move it across. And that converts the lower voltage TTL logic to higher voltage, and that makes it more suitable where there's motors starting and stopping. I'm also using a push button like this one to start, and also to interrogate what's the status is on the linear motor. And finally, I'm using the 6060 push linear motor that comes from M5Stack, and it can be controlled by the computer that we just saw previously. Okay, so communications-wise, I'm using RS-485 at 12 volts. Software-wise, I'm using UI Flow 1 because it won't work on UI Flow 2. And I start off with painting the user interface on the screen of the small computer. And right at the top, I've got the name of the program and the target that I'm aiming for when I move it laterally. So that allows me to replace label 0 with the lateral position. And I can also get the feedback from the linear motor on label 2. So resources, I'm going to use a hat and also a push button. Code-wise, well, we'll go across now and have a look at that on the software IDE on the M5Stack website. So the software I used, the environment, comes from M5Stack. And if you go to their website and select software, you would use UI Flow 1, and you would come up with a screen like this. So we just confirm that's the one we want to use. And you go and select the computer that you're using. Now, since I'm using an M5 StickC computer, I'm going to select the one right in the first row in the middle. And you'll notice on the right, it paints an image of the computer that I'm using. I'm going to paint the screen here. So I would put the title in, and I would put various labels for the parameters that I want to paint onto the screen. I'm also going to use a hat. So if we actually look at hats that are available to us, the one I'm going to use is going to be the RS485. RS485, and there it is. And when I add that, it gives me additional commands, and I'm going to use these as APIs in my program. So rather than constructing a whole program now, I've done it previously, and this is the program. What the program does, it generates random numbers within the mechanical limitations of the motor. That is, the motor can only move in a lateral position only a few centimeters, because it has to do that in the return cycle of the trolley. So let's go and have a look at that in some detail. We'll just push up to our, perhaps first of all, we'll go to the left and have a look at my screen. I've got the name of the program. I then look at the target. I'm going to update label 0 every now and again to show you where my target is. I'm also going to look at the data transmitted from my linear motor, and I'll show that on the screen under label 2. Okay, under setup, I'm setting up the communications to the RS485 transmitter, and the linear motor uses the same. It's got its own little computer on board, and it's able to decode the protocol that I'll transmit to it. And the first thing I'm doing is writing. I'm giving my linear motor an identity, and I'm going to call it 1, 2, 3. Then I give it the new line there, the carriage return, and a new line. I'm setting up my parameters. That is the position. I set the position to 10. The incremental position is 0, and the maximum incremental position is 20. That is, it can only move a maximum of 20 on each return cycle of ALF. The maximum position is 40. The minimum position is 0. And in the setup, I'm not enabling the movement. And I'm doing a count of the lateral position, or the lateral sweeps when we change, and I'm recording those. Okay, in the main loop, if I get data back from the linear motor, I show that on label 2. And if I'm I enable it by looking at the push buttons. So if I give a long press, I'm actually changing the enable. So button B will move laterally, and button A is the button right in the middle of my StickC computer. So I'm using the buttons for control, and I enable it with the dual button. So I'm actually adding a unit. I didn't mention that. So not only do I have a hat, but I have a unit, and that unit is the dual unit. So if you want to see what that looks like, if I select the dual unit, it's this one here, and that goes onto port A of my computer. So you can actually see it's got some commands available. So it looks like this, and there's two of the APIs that I'm using. And that allows me to use event programming. So when I press the blue button on the dual push button, it will enable the motor. And when I press button B, it will interrogate the motor to see where it is. And it captures that and allows me to print it on the screen. Okay, so I think that's most of what I want to show. So you can see the lateral movement, and you can see how I create the random numbers. So the position increment is going to be a random number from 0 to the maximum, the position increment max. And the direction is also random. So it's either going to be positive or negative. And if it's positive, it will add the position increment to the position. And if you move all the way down, you can see that it will do a similar thing for the negative. And it's doing the counts over here. So that's moving the random position. Okay, so that's all done via the loop. So in the loop, see if we can get the main loop. There's the loop down here, and if we have the flag for our enable move is being set, we then move it and then print it. And that's our software to give us the lateral the lateral movement for ALF using the model that I've created. So how did all that go? Well, I got the results that I wanted. I was able to simulate the lateral control of ALF in a uniform distribution. I was able to move that motor in a random to a random position, and the push buttons allowed me to start the cycle, and I was able to accumulate a count of the number of passes of the movements. And I created the random numbers, and my program did this. We'll have a look at how I did the software for that. The second thing I did was a demonstration of the use of the conservation of energy to keep ALF moving up to 1 million passes. So I was quite happy with the results. So to get this project going, I also had to use random numbers. And there are two ways of doing this. I could use software that generated pseudo-random numbers using software like this. So it was done on Windows with Python and using a IDE called Thonny. And the second one that I generated was the plot and the histogram. So to look at the objectives for the plot, I want to generate the pseudo-random numbers and show them graphically. So I'm going to do this on a Windows PC, and my code looks like this. So I'm going to use both the random and the matplot library. So I'm using a mean of 100 and a standard deviation of 50. Then I just plot the results. And they look like this. These are the random numbers generated from 0 up to 100 passes. So you can see that there's a distribution there. And we can go a bit further and see how they're distributed according to the location. So most of them will be in the middle, but what I do get is a Gaussian. I did this originally in Microsoft Basic, and that was done 43 years ago. So we might have a look at what that looks like on my references. So the book that I used to do that was this one, Basic Program for Scientists and Engineers, and it contained the algorithm written in BASIC that I used on an Epson HX20 computer. So this is a model of ALF that was made 43 years ago by the Department of Main Roads. I was one of the lucky ones that was presented with the model, and I don't have the trolley, but the idea, it was able to demonstrate the conservation of energy on ALF from the launching position up here to the loading the pavement. Well, might have a look at that. Open up the electrical push that it gave. So while it had potential energy at this end and kinetic energy in the middle, it needed a bit of a push, and it got that push by this electromagnet. So you also added a battery. Now the trolley had rotated on the rails, and it had a magnet. So when it went through the electromagnet, it was a bit like a motor. It was given a bit of a push, and it was able to get to the other end, then return. In this demonstration, we're looking at the conservation of energy, one of the principles used by ALF. So what we're doing is converting the potential energy, which is got at the moment. It's then converted to kinetic energy, but it's also been given a bit of a push. Otherwise, it wouldn't be able to get back up again. So the ball is demonstrating the way that ALF would currently return and then load. So it's loading the pavement, and while it's loading the pavement, it's getting a bit of a push to the trolley. So what we're going to do is convert the potential energy that we have here, and there's a small electric motor that gives it a little push. So while it's down here, it still has enough energy to complete the cycle. So there's lots of kinetic energy here, enough to get back to its original launch position. So we're going to launch it. The electric motor is just inside. You can hear the motor ticking across. So let's lower the ball. And if this was ALF, our loading position would be here, and the return would be this loop here. So let's give it a demonstration. In this demonstration, we're going to examine the lateral behaviour of ALF. And this is simulated using a truck with various weights on it. And here I'm using a stepping motor on the bottom that converts the rotary motion to linear motion. So in this lateral behaviour, I'm going to randomly move the truck laterally with a uniform distribution. And the final goal is to use a normal distribution. So it's using a M5Stack StickC computer with a RS485 communications unit, and that's connected to a push 66 module with the stepping motor, and it can then, using the worm drive, provide that linear motion for me. Okay, let's give it a demonstration. So we'll press the button, and we're now getting motion. So it's now seeking a random position laterally, and if it can't move it, so ALF could only move a certain lateral position. If it took too long, it would then crash. So we had to be careful not to exceed the maximum limitation of ALF. And it's telling me on the computer the target. So at the moment we're about 21 centimetres from the midline position.